Welcome, and thank you for joining this webinar. From Connectivity to Understanding, the Semantic Future of AI Communications, prepared by the Alpert Research Team. Understanding semantic communication, or SEMCOM, is a strict strategic imperative. It literally represents the foundational shift required for the networks of the 2030s. If the receiving machine gets a transmission where 90% of the original bits, all the visual packing peanuts, have been intentionally thrown away, how does a telecom engineer actually measure success? For 50 years, the ultimate dashboard metric for a network operator has been the bit error rate. You send 1,000,000 bits, and if only 2 bits get flipped by static, you get a gold star. But if we aren't counting bits anymore, what replaces Shannon's math?
This brings us to the new underlying science, semantic information theory, or SIT. We are entirely moving away from measuring bits to measuring meaning, and the foundational mathematical concept that makes this possible is called synonymous mapping.
Let's use a really simple example to illustrate how backwards this is from classical engineering. Take the words car and automobile.
Okay.
In classical bit-centric systems, if you look at their ASCII binary codes, the ones and zeros that make up those letters in a computer, they are completely fundamentally different. If a classical network drops a single bit and accidentally turns the word car into tar, the transmission is ruined. The engineer logs a failure.
Because classical Shannon entropy measures the uncertainty and the exact syntax of the symbols themselves. It cares about the spelling.
But in semantic information theory, the words car and automobile belong to the exact same equivalence class. Because the vehicle's braking algorithm reacts identically to both words. It doesn't care which one you use, the result is the same. Semantic entropy is actually much lower than Shannon entropy. Because multiple vastly different bit patterns can convey the exact same meaning, there's inherently less uncertainty about the meaning than there is about the syntax.
Which redefines the telecom business entirely. Network operators are currently redesigning their command centers. They're moving away from traditional metrics like bit error rates, or BER, and peak signal-to-noise ratio, PSNR. They are adopting semantic KPIs. It allows operators to extract vastly more utility and action out of the exact same limited physical spectrum, which drastically lowers the cost per bit for actionable intelligence.
The sources state that semantic channel capacity can mathematically exceed classical Shannon capacity.
I know, it sounds impossible.
How is that possible without breaking the laws of physics? Shannon's limit is like the speed of light for data. You cannot physically push 10 gigabits of data through a 1 gigabit pipe.
It's a brilliant paradox, and you are right to be skeptical, but we aren't breaking physics at all. We are exploiting semantic redundancy. Imagine 10 different 4K security cameras all looking at the exact same stop sign at an intersection, just from slightly different angles. Syntactically, under Shannon's rules, those are 10 drastically different, massive video streams. If you try to push all 10 raw videos through a local cell tower simultaneously, you hit the Shannon capacity limit immediately. But semantically, what is the actual actionable value of those 10 massive video streams to a connected car's braking system? The value is just a single binary state. Stop. That's it. In a semantic network, we collapse the state space of the data before it ever enters the pipe. We extract that one vital semantic token, the command to stop, and we transmit only that tiny token. So we effectively widen the channel through contextual intelligence. The channel's capacity to deliver actionable intelligence vastly exceeds its physical capacity to deliver raw bits.
We aren't making the pipe bigger. We are just drastically reducing the size of what goes into the pipe by boiling it down to pure meaning. So if we are tossing out the bit error rate dashboard, what are the new vital metrics that a 6G network engineer will actually be tracking?
The primary semantic KPI replacing bit error rate is task success rate, or TSR.
Meaning, did the machine actually do what we wanted it to do?
Yeah. If the network sends a command to a robotic arm to pick up a fragile silicon wafer, the network doesn't care if a few pixels of telemetry data dropped out over the Wi-Fi. The only question that matters is, did the robot grab the part without shattering it? If yes, the transmission was a 100% success. Another critical metric is latency to meaning.
Traditional latency just measures the milliseconds it takes a packet to fly through the air from the cell tower to your phone.
L2M includes the cognitive processing time because you aren't just sending simple data anymore. The AI at the receiving end has to actually think about it. It has to unpack that semantic token and decode the intent. So L2M measures the total time from transmission until the moment the receiving machine fully understands the command.
New metric is the age of incorrect information, along with the value of information.
It's a crucial concept. Imagine an industrial boiler in a chemical plant. It sends a critical temperature reading of 300 degrees. But there's a network jam, and that data packet gets delayed in a router for an hour. Classical 5G network finally delivers it, checks the bits, sees they are in perfect order, and logs a completely successful transmission. But semantically, that hour-old reading is not just useless, it is actively dangerous if the safety systems rely on it. Its age of incorrect information is simply too high.
Under classical rules, the network is perfectly happy to deliver an old, deadly message as long as the spelling is correct.
The new semantic network dynamically balances all of this. It constantly weighs latency, task error probability, and communication cost using a multidimensional mathematical tool called a goal-oriented tensor. It manages these variables microsecond by microsecond, deciding what information is actually valuable in the moment.
Okay, the math on the whiteboard is elegant. It proves we can squeeze vastly more meaning into a saturated channel.
From Claude Shannon's rigid mathematics in the 1940s to the AI native architectures rolling out in the next few years, the core takeaway is clear. Prioritizing the transfer of meaning over the transmission of bits is the absolute cornerstone of the next era of global connectivity.
It's the only way forward.
It is the only mathematical, physical, and economic way we can scale successfully into the 2030s. Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their strategic implications. Click the links below to learn more. Thank you for taking this deep dive with us. Keep exploring and keep asking questions about the hidden architecture of our digital world.